Thank you very much, Yuri. Welcome to everybody. Actually, it's really nice, as Nick said, to be in a room with so many friends, so if you don't mind, I will do exactly what he did. So, waving is good. Hi, Bartek, how are you? This is going to be a very different kind of talk to the ones that we've been hearing so far. Most of the talks that we've heard so far have been very, very deep. Sometimes have very, very deep and very broadly applicable. But this talk is going to be very shallow. I'm going to still follow Nick's dictum and try to overwhelm you as much as possible, but I'll try to do that by breadth rather than depth. So some of you will know Maple very well, and some of you are quite new to it. MapleSoft has supplied licenses. So Nadia Sid is sitting in the back here. She's from MapleSoft, the local office, and you will be able to ask her questions at coffee, particularly if you have some issues with the license or anything like that. Please talk to her. If you're new to Maple, there is a new users tour. You can click on the once you've started it, you can click on the clicking while you're up here is a little bit hard. It'll give you videos and tours and various other kinds of things. I'm not going to do that. I'm actually going to start with a tutorial that was designed to appeal to this audience. So this is a workbook which was supplied in the link publish.uwo.ca under my website. Actually, let's use this one. So I have 22 different slides. Bartek?
Yeah, what's the best way to get this file?
So you go to publish.uwo.ca/r Corless. The link was in the email that, no, the link's on my abstract on the INI website. And this file is called Introduction with Bohemians. I'm not going to talk about Bohemians today. Tomorrow is the Bohemian Day. And this is a workbook, and it contains all of the worksheets that we're going to be looking at, and plus some code. But before I start in this, I'm going to allow myself a 3-minute reminiscence. I'm getting up there. Don said, well, I'm 40. I'm old now. I'm 60. I get to do the ancient story. So I'm going to tell you a little bit about my history with computer algebra. Not strictly because I want to reminisce, although I do want to do that, but because it actually should connect the kinds of things that you're interested in with the kinds of my experiences and may help to motivate why you should listen to me. So my undergraduate was math and computer science at the University of British Columbia in Canada, both math and computer science. So in the computer science, I worked with Jim Vera and Uri Asher and did numerical analysis. In the pure math side, George Maxwell and David Boyd taught me algebra and number theory. So I began my career kind of poised between the worlds of analysis and algebra. George Maxwell said in the 4th-year algebra course when teaching rings, fields, and he said, ideals are just gorgeous. A principal ideal, just absolutely fabulous, but you'll never find a use for it. Don't worry about it. It's not useful for anybody. In my very next year, which was when I went to Waterloo, I took another course in numerical analysis from Keith Geddes. He did his PhD in approximation theory, so we worked with Cheney, and so I learned numerical analysis and approximation theory from Keith Geddes. And he said, we'll have a course next term, this would be January 1981, in computer algebra, and I think you'd be interested in that. And during that course, I learned that ideals are actually really important for making computer algebra systems run. It's actually required in order to make the code go fast. So my well-intentioned and very good algebra teacher, George Maxwell, was completely wrong when he said that ideal theory was useless. It's actually fundamental for making code go quickly. You need, for modular methods, and modern computer algebra is necessary. So there's my connection with computer algebra, and my connection with Maple is during that course. This is 1981. There was no Maple at the beginning of the course. We studied CAMALS, the Cambridge algebra language invented here, David Parton and John Fitch, and Reduce and Altran and Formac. But by the end of the course, there was Maple. Keith Geddes and Gaston Gonnet and Morven Gentleman had invented Maple by the end of that term, by about March 1981. So we're coming up 39 years on a computer software project, and 39 years is an enormous time for software. So MapleSoft has survived as a viable product for a long time, and it's done so on the basis of some very deep mathematics. So that's the connection that I wanted to make with my background and what was going on here. Most of you are analysts. Some are really good at algebra, but there's some serious algebraists in the other program. Maybe there are a couple of algebraists here, but most of you think mathematics from an analysis point of view. And it turns out that there is a fundamental difference between algebra and analysis, and you'll see that play out during here. I got my 3-minute reminiscence in and actually did some connections here. So let us start the slideshow. I have too much essential tremor in my hands to use the mouse to, sorry, I forgot to increase the size a little bit. So I can't use laser pointers. So I really like the fact that I've got a big pointer here. And I'm sorry that I don't have a keyboard that has F11. So I have to do the V. There we go. That's a little better. This talk was prepared as a Maple workbook, actually, and containing several worksheets and some code, but it's prepared with advice from Jürgen Gerhardt, Dave Linder, John May, and Eric Postma at MapleSoft, and also with the advice of my colleague and friend David Jeffrey, who's the director of the School of Mathematical Statistical Sciences at Western. I've done my best to make sure that there's no errors in here, but if any that are there are my fault. If you take one thing away from this talk, I want you to take the final slide. I've got a link to a book called Modern Computer Algebra by Joachim von Zurgathen and Jürgen Gerhardt. This is a book of the theory of the algorithms underlying computer algebra. It's an absolutely fabulous book. So if you take nothing else away, take that book away. Cambridge University Press, and if you go to the website while you were here and using your visitor ticket, it looks like you can read it for free. I don't know whether that's generally true, but the PDF is there, but it's absolutely lovely book, 3rd edition now. Why? Learning computer algebra systems takes time. Most of you, how many here have never run a MATLAB program in your life? No one. Well, yeah, sure. MATLAB itself is not very hard to pick up, but it takes some time on its own. There's some really interesting things you can do with it. It takes time. Learning Maple is not that much harder, but it is a little harder. And in fact, it's so similar to MATLAB that there's some opportunities for confusion. Equals in Maple means something different than equals in MATLAB. So you have to do some shifts. So why take the time to do it? There's that activation barrier to get up and over. So Nadia's a chemist. She knows about activation barriers in here. Well, my reasons, I don't know about your reasons. My reasons include computational discovery. So computational discovery is also called experimental mathematics. And I recently had a conference, 2 conferences at Western, where we combined philosophers and computational scientists. And the proceedings are out now. ACMES is the, we started from the acronym and worked backwards to Algorithms and Complexity in Mathematics, Epistemology, and Science. There's a paper by Yuri Mariuszewicz. He's attacking the Riemann hypothesis experimentally at the moment. Experimental mathematics is a viable mode of exploring mathematical interests, and general purpose tools to do computation, mathematical computation, are extremely helpful with that. So ChepFun is the most significant development in this kind of experimental mathematics in the last, well, it's 10 years old now. ChepFun is 10 years more, oh my goodness. And now we have a ProxFun, which I just learned about the other day. So this is interesting, that other ways of doing exact computation, or very nearly exact computation, by approximating with these things. These tools are useful for everybody. I think. In any case, they're useful for me. And so I'm going to talk to you about some of the ways in which you can use computer algebra, and some of the ways in which it's not going to help. I should have followed Nick's example before, but it's on. It should be the abstract.
The second abstract.
Oh, the abstract for the second. Okay, for Friday's abstract. Thank you. I knew I put it in there, but I didn't realize I put it in there. Nick, I tweeted yesterday about you using the poll for harmonic analysis. So we're going to be using. So what you can and cannot do with computer algebra. You can solve some mathematical problems exactly. Okay, Kahan puts it really nicely. He said, have you ever asked a computer algebra system a question, and then as the answer goes whizzing by, you say, you wish you hadn't asked? Sometimes the answer is extraordinarily complicated, but sometimes the answer is 0, and that's what you're looking for. Sometimes the answer is 1, or sometimes the answer is really simple. Anyway, here's another of Kahan's example from a beautiful paper, 1980, Handheld Calculator Evaluates Integrals. Integrate 1 over 1 plus t to the 64th for t going from 0 to 1. So the capital I means just write an integral symbol. Do nothing. It's an inert integral. Equal sign says, oh, this is an equation. Don't do anything. I'm telling you about an equation. This is not assignment. It's just an equation. On the right-hand side, we have a lowercase int. And here I have to say the hardest thing about learning Maple is the syntax. I'm sorry to say that Mathematica has a better, more uniform syntax. So once you learn the style, which seems a little bit alien to me, but once you learn the style, it's fine. Maple has evolved over nearly 39 years now, with hundreds of people contributing to the central way, and they have done so in different ways. It's done so in different eras where different conventions were in place. So this convention about capital I being inert and lowercase being active holds for a lot of Maple, but not all. Unfortunately, this just means you have to learn. And I think it's worth it to learn this, but there is a certain barrier involved in learning these things. In any case, you ask Maple to do this integral, it says, no problem. I can do partial fractions. It's just a sum over, that's just 1 over t minus product of t minus some roots of unity. But away we go. And it writes it, the answer is the sum of logarithms, difference between 1 and 0. Of course, these are complex logarithms, but that's okay. Root of is a Maple innovation. It just says, oh, it is a root of that particular polynomial. And when you have the sum over r equals the root of this thing, that means the sum over all roots. And it doesn't matter which order you do them mathematically, you just have to sum over all of them. And it's just the residue calculus is being used there. Whoop, out it goes. In Kahan's paper, he transforms that into sines and cosines, so it looks real. But that's fine. I'm perfectly happy with that answer. If you had the power 1024 instead of 64, it's still just a root of sum of root over all the roots of that polynomial. It's more complicated, some over 1,000 roots, but there it goes. By the way, with 22 slides and at this pace, I am not getting through all of this stuff. There's no way. It's okay. I'm going to be cut off at the end, and we'll go for coffee and we can continue discussion. So next line. Capital S sum just means write a sum is equal lowercase sum, and this is sum of minus 1 to the power k over t to the n times k plus 1 over n times k plus 1, sum from k equals 0 to infinity, assuming t is between 0 and 1 and n is positive. So the assumptions that we have about symbols come from our culture. A lot of us think any variable that starts with I, J, K, L, M, or N is an integer. That's the old Fortran convention, and it still survives. So I didn't tell Maple that N was an integer. I did tell it was positive here. But in fact, it doesn't matter whether it's an integer or not in this sum. This sum, Maple says, I know how to do that sum. That's a Lurch phi function. How many of you have ever used Lurch phi? 1, 2, yeah? Dan? Oh, wow, this is the correct audience for Lurch phi. Of course, it's a hypergeometric function, and Maple knows quite a lot about it. But in particular, it's an answer, not a question, to Maple. So this is already more powerful than first-year calculus people or second-year calculus. The sum of this thing is outside the reach of most people who are just had 1 or 2 courses. But it's a hypergeometric sum, so no problem. And you might notice that if I replace 64 by n, and I expand that as a geometric series, and I integrate term by term, the sums that I get are these ones. So this is an alternative way of answering that integral question. This is between a difference of 1 times Lurch phi of minus 1 over n, and 0. So the fundamental theorem of calculus gives us a one-line answer in terms of Lurch phi for this thing. Why doesn't Maple do that instead of the root ofs? It's because Maple also is in use for teaching purposes, and first-year students would be absolutely horrified if they integrated 1 over 1 plus t cubed and got a Lurch phi function out of it. You want ordinary partial fractions to play a role. All right, well, here's an oscillatory integral, not a hard oscillatory integral. This is one of the easy ones that Arya dismisses with a wave of his hand. These are easy. So integral of cosine omega t over 1 plus t squared, t going from minus 1 to 1. And Maple says, oh, I know how to do that. That's in terms of sine integrals and sinches and cosine integrals and coshs. All right. I want to know what this is when omega is 13. The Corless principle at work again. Thanks for that, Nick. If we just simply ask for the floating point evaluation, eval f means eval to over floating point. Eval without an f means evaluate. Evaluate the right-hand side of equation 3.3 with omega equals 13 means substitute omega equals 13 into the equation and evaluate it. So you get minus SI of 13 plus O. Early convention of Maple, lowercase italics got translated to uppercase. So the imaginary unit in Maple is capital I. You can change that. I can say interface imaginary unit equals underscore IM. I can do whatever I like with that. But I'm just used to capital I for the square root of minus 1 now. And okay, we can do that. Anyway, we have this. If we evaluate this, the default precision is 10 digits of precision, and we get a negative answer. And it's, in fact, the wrong answer. If you evaluate to 50 digits, you get the correct answer. And 50 is enough because each of these things, the SI of 13 plus 13i and sinh of 13 is about 10 to the 9th. So we lose about 10 digits of significance if we evaluate this expression by just by cancellation in there. So you have to realize that an exact answer might be subject later to numerical error if you use it numerically. So sometimes it's actually better to evaluate this thing. Eval_f of capital I int now says, oh, take that inert integral and apply numerical integration to it. Keith Geddes and Greg Fee wrote a beautiful, very, very high-powered quadrature routine for Maple that uses series at the singularities. It can handle quite sophisticated series, does exact integration of series terms, and then Clenshaw-Curtis quadrature where things are smooth, and does quite a nice job. And Nick, many years ago, said that the central mission of numerical analysis is to compute things that are typically uncomputable from an analytic point of view and to do it at lightning speed. I think that's true of computer algebra as well. A lot of the things that I've shown you here are actually impossible. It is impossible to do numerical integration. Kahan had a proof of that in that paper. It's impossible to do symbolic integration. We all do it anyway. I am not going to tell you anything about the linear algebra package. In the Handbook of Linear Algebra, this is the first edition, chapter 72 by David Jeffrey and Rob Corless, so that would be me. Linear algebra in Maple tells you a lot about linear algebra in Maple. The second edition, we don't have a physical copy in the library, but there's an electronic copy in the repository just across the way, so you can go in and sit at the legal terminal and read the PDF version of the Handbook of Linear Algebra. This is an amazing resource, though, and there's a chapter by Mark Embry on pseudospectra, chapters by Anne Greenbaum on large systems. There's lots and lots of useful things in this book, and it's highly recommended that people buy it. This is a little advertisement for tomorrow's talk. This is an example, my first example of Bohemian matrices, the Mandelbrot matrix. There's a little code box hidden up here. I've got some Maple program that Piers Lawrence wrote, and I stuck it in there, and I've just executed this code here. And we have a 1,000 by 1,000 matrix. Compute its eigenvalues, real time 2 seconds, CPU time nearly 4 seconds. This is just my little Surface Pro. There's 4 processors in there. There's a little bit of parallelism that's being used behind the scenes, which is great. MATLAB on this same machine takes 4.5 seconds for this thing. So Maple's numerical connection to the NAG is actually pretty good. It's not as complete. MATLAB has much better facilities for sparse matrices, particularly if you want the singular vector of the M13. You really want to use MATLAB for that. Before I talk a little bit more about what's going on, almost everybody in the room is a big fan of double precision. Just blindingly faster than arbitrary precision. Why? In my opinion, IMO. How do you do, fellow kids? In my opinion, it's because arbitrary precision arithmetic requires unpredictable amounts of memory. And so you have to include memory allocation, an increasing memory allocation, and then garbage collection afterwards. And all of this add up to a factor of 300 to 1,000 in terms of speed. But sometimes it's necessary. There's a beautiful paper of Bailey and Borwein that says that actually, rather than develop a whole collection of new software or new algorithm or something, if you want to solve just this one problem, got a big hammer, put digits up to 100, and the 100-digit precision or 1,000-digit precision in Maple is perfectly easy, perfectly possible. But sometimes not necessary. I really like the square trap trick. So here's the derivative of gamma at 13 done by the square trap trick. In 10 digits precision, here is the derivative of gamma at 13 point, and floats are contagious. If you input a floating point number to a function in Maple, it will say, oh, you want the floating point value, and we see we have the same derivative value. This does the derivative exactly and then evaluates the psi function and the gamma function there. What this says to me is that the gamma function has a very good, relatively accurate imaginary part in order to get this accuracy. If we want more digits, you can just say eval f to 60 places, or you can set the environment variable digits to be something else and do something more. This help page is question mark numerics. If you type that into Maple, you get a really interesting page on the details of how Maple implements its numerics, which is not maybe what you would expect. Yes. Would they tell everybody that? I don't know. Yes, that page is quite detailed, and there's a Maple numeric model which is explained. But I actually want more details than that, and they're amenable. So if you actually email and ask, they'll give you as much information as you want, I think.
Okay, is it possible to do interval arithmetics in
I'm sorry?
Is it possible to do interval arithmetics?
Yes, I wrote the first interval arithmetic package in Maple back in 1993 with my undergraduate student Amanda Connell. That package has long since been superseded by a package called intpacx, which is a third-party thing, but much better than the code that I wrote. Arbitrary precision interval arithmetic is quite interesting for people. Fredrik Johansson has a package called ARB, which I recommend that you have a look at if you're interested in arbitrary precision interval arithmetic. He's done an amazing... He's also got the best title for a collection of functions, of results about mathematical functions. He calls it a function grimoire. Never mind a handbook. I want a grimoire of linear algebra. He's got the function grimoire, so go and have a look at Fredrik Johansson's work there. Series. Lots of people love series and asymptotics. Maple's series have been generalized since the beginning. You have Taylor series, Laurent series, Puisa series. Here's a Puisa series for the square root of Lambert W, and it just says, no problem. Powers, fractional powers. Series, I like this. Series can be reversed. So many people know the Lagrange inversion theorem, and so that they can take a series and reverse it by hand. You don't have to do that with Maple. You say solve. Solve y equals this series for the thing that's in the series. Is, oh, you want a solution that's in a series, and it'll reverse the series for you. That's really useful. I like that a lot. Asymptotics. If you say asympt of the function right omega, everybody knows the Lambert W function. I put some more posters out so that there was only one left. Now there's more. But the right omega function is named for Sir Edward Maitland Wright. Is related to the Lambert W function. And in fact, it's w of e to the x. But you choose the branch correctly. And it turns out that it's nicer at infinity because this function is asymptotic to right omega t is asymptotic to t, where Lambert W is asymptotic to log x. So Lambert W of e to the x, you compute e to the x is too big, and then you take the logarithm, you're back to where you started. You might as well use the right omega function. So asympt of right omega says, oh, we know that. But if you ask for asymptotics of Lambert W, it says, well, Lambert W is an answer, not a question. What are you talking about? W is asymptotic to W. There's a switch. You can change that, but I'm perfectly happy with that. John Shackle and Bruno Salvi have a really interesting collection of papers on asymptotics with different scales in it based on work of Hardy. So have a look at those links. We can find those. And after Andre's, no, sorry, it was, you didn't give the talk. Who gave the talk? Nick. Oh, yes, Nick. Yes, I knew that. Where are you? Where did he go? There he is, yeah. I just had to try the quadratic Pade. Of course, it's in Maple already. It's Hermite Pade is part of the NumApprox package. So there's an approximation theory package. I said Keith Geddes did his PhD thesis in Chebyshev Pade things. So there's lots of approximation theory things there that are old. But if you want to do Chebyshev Pade, one line, oh, here's a multiple assignment. L, M, and N get assigned 5, 5, and 5. My pet peeve is the use of a lowercase l as an index. To me, and in typewriter fonts, there's 1 pixel different to a 1. So no, don't do that, please. So script L, well, all right, this is ASCII. So ELL, L, M, and N are 5, 5, and 5. P, Q, and R are add. This is not the summation thing that I was talking about. Summation before it does symbolic processing, trying to figure out an analytic formula. Add just says, no, there's a bunch of things that I want you to add up really quickly. So add AK is an unknown coefficient times Z to the K. Z's a symbol. If you type a symbol into MATLAB without first saying sims, it says, well, I don't know what unassigned value. It's the default in Maple is that if you type a name of something, it's going to be a symbol for something you want to know later. So AK is a symbol, Z is a symbol, and we sum from 0 to L, 0 to M, 0 to N. So I've got 3 sets of variables here. I want the quadratic Pade approximation to Lambert W. I take the series of P plus Q times F plus R times F squared with respect to Z to a certain order. I set up and solve the equations. The equations are setting the coefficients of the ansatz to 0. So I want each of those coefficients to be 0 from K equals 0 to L plus M plus N plus 1. I solve them. Solve is a very powerful routine. It was originally written by Gaston Gonnet. I was going to advertise this talk as not your parents' Maple, but Pedro might be watching, so not quite true. Gaston's influence is still here. And solve was very powerful when he first brought it in. It's become even more powerful now. You just give it the equations, and if it can solve them, it will. So we have the solution. Oh, semicolon means do it, but don't print the answer. I don't want to look at it. So just like semicolon in MATLAB. Semicolon in Maple means do it and print it. So there's one of those faux amis that causes trouble. So if we evaluate P, Q, and R, this is a list. So the first entry is P, the second one is Q, the third one is R, and they're separated by commas. There's a comma there, which is impossible to see another comma unless you're paying attention. And we find one unassigned parameter. It chose C5. If we chose C5 to be this ugly number here, everything would be integers, but I don't care. And if we evaluate the ansatz at the solution, it says the residual is of the order Z to the 17, which is what we want. And the computation is fast. I said this was impossible. One of the things we want to do is simplify. There's a lovely paper by Dan Richardson called How to Recognize Zero. And he says, the history of zero recognition is somewhat confused by the fact that many people do not recognize the problem as a problem at all. And how could you not recognize zero? Zero is zero. Well, is log of tangent of z over 2 plus pi over 4 minus arcsinch of tan of z equal to 0? That's the kind of question you might ask a complex variables student if you were being mean. If we plot that on the interval minus pi over 3 to pi over 3, this was with digits 15, and we see rounding error. Everybody in the audience is convinced that, okay, on that interval, it's 0. What about over the complex plane? So we plot, this is one way to plot a phase diagram. So the color equals the argument, and I'm actually doing a three-dimensional plot, but with coloring the plot by the argument, and I'm looking at it from the top down. Orientation equals minus 90 is 0. I'm looking at this 3D plot from the top, and we see things that are not 0 in the phase plot. And they're really not 0. Height of 1. But in the interval minus pi to pi, it is 0. So this question is not just an algebraic question, it's an analytic question. And some of the analytic answers or partial answers involve something known as Shanuel's conjecture, and I urge you to read Dan Richardson's papers about that. Okay, for heuristics, there's things like combine cos t cubed times sine t, and combine it knowing that it's trig functions. Oh, well, that means you want the multiple angle formulas. That's a useful tool. I like combine. Collect is another really nice one. Collect, and you can apply whatever function you want to the deal. But you don't want a default of expanding, because a plus b to the 1024, if you expanded that, it's gigantic. And you don't want a default of factoring, because a to the 1024 minus b to the 1024, if you factored that, you have 4 or 5 lines of factors. So there is no default that works well even for problems. So Maple leaves things alone until you say simplify or collect or combine. It leaves the simplification tools on the part of the user. And at this moment, humans are still better at simplification than computers are. It's an undecidable problem. I went back to UBC to do my PhD. I did my PhD with a man named G.V. Parkinson, Jeffrey Vernon Parkinson. He was a big ideal fluids man. I learned a lot about conformal maps from him. And I very excitedly showed him the Maple can do residues. Takes all the fun out of it, he says. Okay, well, yeah, but it's still useful. So if you ask for the residue of the cotangent of pi times, oh, there's another crazy thing. Capital Pi is Maple's language for the ratio of the circumference to the diameter. The residue of cotangent of pi z at z equals n, assuming n is an integer this time. It's 1 over pi, and that's correct for all integers. So I like the fact that Maple can do some residue computations with symbols and assumptions. That's actually very powerful. Probably can't do them all, but it can do a lot. I don't know. I do not know the details of, so some knowledge of the trig functions must be encoded. In fact, we'll look at some of the encodings for knowledge about functions in a little bit. But yeah, it's surprising that it can do that. Here's another thing that's a bit surprising. If you work with algebraic numbers a lot, you get tired of writing root of z to the 7th plus z plus 1. So we say alias alpha is root of p of z. That means alpha is any root of this polynomial. So the only thing we know about alpha is that alpha to the 7th plus alpha plus 1 is 0. Now if we ask for the residue of 1 over p at z equals alpha, it says 1 over 7 times this root of to the 6th plus 1, which is correct except for the index. The index now says, no, it's a particular root. Fine. That's a cavil. I'm not worried about that. But if you ask for the series of 1 over p at z equals alpha, it says, oh, yeah, that's 1 over alpha to the 7th plus alpha plus 1, which is infinity. It's got it wrong. Gaston knew that perfectly well, and he had the suggestion of the way of doing it, which was you need to use your own test zero in there. If you're going to be working with algebraic numbers, you should strengthen the zero tester, and so you do that by using a normalizer that's built for algebraic numbers. A normalizer will always recognize 0. A normal form is one where 0 is only represented by the 0. That's it. A canonical form is if everything in your class of functions has its own unique representation. A normal form is something where 0 is guaranteed to have only one representation. So in something where you have a normal form, 0 is always recognizable. So, okay, we tell test 0 that we're dealing with algebraic numbers, and series remembers its previous results unless you tell it to forget it. So now we do series 1 over p at z equals alpha. It says, 1 over 7 times alpha to the 6 plus 1, z minus alpha to the minus 1. So it gets the correct Laurent series in that case. There's another series package. This was done by Bruno Salvi of the generalized series thing. Most of the functionality for multi-series has been moved into series and ASM by now, but sometimes if series fails, you might try multi-series on something, and actually it does quite a nice job on this. Here, the second term is a little bit more complicated. Multi-series is actually simplifying things in a nice way, so I like that. I'm glad I got to this slide. Differentiation, most people learn about differentiation in high school. How can there possibly be any interest in having a program in a computer do your differentiation for you? Yay, the derivative of sine is cosine. Okay. Alternative syntax if you want to evaluate it. D of sine, derivative of sine, evaluated at 3.14, this minus 0.9998. Yeah, great. I'm happy with that. Here's something new. Diff of sine x over 1 plus x to the nth order. I haven't told it what n is. It's assumed that n is an integer if you give it that syntax, $n. It's a sequence of x n times, but I haven't told it what it is. It says, aha, the nth derivative of sine x over 1 plus x can be written in terms of incomplete gamma functions. I didn't know that. I can differentiate sine of x over 1 plus x quite a number of times, but I wouldn't have known how to do it n times unless you told me what n was first. Here's program differentiation, automatic differentiation. I make a procedure p, which just a polynomial. I have a for loop here for k to 10, s goes to s plus k times x to the k, and return s. So there's the procedure that evaluates a polynomial. And then I say dp is d, the same d that you apply to functions up there. And it says, you want me to differentiate a procedure. And it writes another procedure that does the same thing as the other one, but also computes the derivative and returns the derivative. I like that. That's useful. There's also reverse mode gradients in the CodeGen package. So this is actually quite a powerful thing. Here's my favorite. Take a half-order derivative. In this audience, I bet probably half of you have used fractional derivatives in anger, as they say. So, but I like this. The fractional derivative of sine of x squared, the half-order derivative, is this 3,4 hypergeometric function times x to the 3 halves, and you can plot it.
Is that left-sided or right-sided?
It is left-sided. I'm sorry, what?
Riemann-Liouville or Caputo?
I prefer to call it another name, but Caputo. Yeah. Davison, Essex. That's because I learned it first from them. But yeah, it's a Caputo. And you can fuss with that if you like as well. Let's escape from here. I've got 10 more minutes left. I can talk more about integration. I can talk about ODEs. I can talk about elementary and special functions. I can talk about plotting. I can talk about phase plots. I can talk about code generation. Actually, let's do a quick one on code generation. So lots of us know one language or another. We say we might want to write a MATLAB program from a Maple program. You want to build something, and there's ways to build programs automatically in Maple, just piece by piece, put them together in a procedure, and then translate it. You can translate it to Fortran, to C, Julia, I have no idea whether that's good Julia code or not. I'm not a Julia person. Python, whatever you, it's a very powerful trick.
None of them are good because you wouldn't want to calculate x over k.
That's true, actually. But at least it's a translation.
Yeah.
If you want to do good work, good code, well, there's an older package written by Michael Monaghan. Hello, Mike. Called CodeGen instead of code generation. This is actually an older package which does things to optimize. So it will take an expression and walk over its DAG, find repeated sub-expressions, and give you an expression sequence which will evaluate that thing efficiently. So it's a way of unrolling loops for a bunch of things. And tomorrow we'll see a case where we'll actually do this. And you can find out that the cost of this thing is so much. Old models of cost, right? Because most of this stuff actually happens in the shadow of memory access nowadays, and there's no measuring of what the memory access of these things is. But it's a step. Over 39 years, people have developed significant amount of code for Maple. There's 148 current packages and 13 of the old ones that we don't want you to use anymore. The computer algebra or computer science term for that is we deprecate those packages. We're still there for backward compatibility, but they're like an anchor on your leg as you're being dragged into the... So I'm not allowed to tell you that there's an older package than linear algebra. You must use the linear algebra package. Okay. Computer algebra systems live with polynomials. And they live with multivariate polynomials. And multivariate polynomial stuff is amazingly interesting. I like to do it by eigenvalues. I'm not going to do that. I got asked about calling MATLAB from Maple. So we'll do that at the end here. You can, if you have MATLAB on the same machine, a valid license, you can say with MATLAB and eval m and give it a generic MATLAB command. And then say, oh, get me the result of that. I believe this will work with chub funds. So we can now, as I say, build a ship in a bottle, working way over there, making little changes over there, and then taking the results back this way. So if you want to do that, you can.
Isn't there a package called MTN which imports similar commands or commands from MATLAB? Not really relying on installation of MATLAB, something like that.
So it's called MP what?
MTN.
Not one that I've used. So let's look. There's MATLAB, MTM. MTM is a collection of commands to support the Maple toolbox. I don't even know what the Maple toolbox is. And I've been working on Maple for 39 years. And this is not surprising that people will know more about some parts of Maple than I will. I do the things that I do. I like to do a lot, but wow, there's a lot. So that was the result of a help command. I did question mark, index, comma, packages, and we did that. Where to find more information? For serious algorithmic information, see the book Modern Computer Algebra. Now, I did click on that. Oh, come on, click on that. Follow. I really meant follow. So my book is now 15 years old. Do not read my book. It has, some of the programming stuff is okay, but there's a lot that's changed. And so it's much better to read the programming manual. If you want to find out about how to make Maple do things quickly and efficiently, there's a page called Efficiency, to help efficiency. Maybe I'll get around to writing a third edition. Who knows with that now that I'm retired. And with that, I'm done. Thank you very much. Ty.
Are you aware of a Maple functionality that does FFT in
Yes.
arbitrary precision?
Ooh, that's a good question. They have an FFT package, and
They're using floating point.
well, kind of breaks the on the one hand, you want to do it fast, and then you want to do it high precision. That's going pulling the opposite direction. I don't know if they did that. I do know that they have the tools to, and as far as I know, they underwrote all of the NAG library with arbitrary precision. So I think it would have happened automatically. I've never tried it, but I suspect that it's there, and I think it just runs more slowly than you expect if you tried it. Alex.
You said that ideals are absolutely essential. I think you meant more than just for Grobner-based.
Oh, yeah.
You also meant for the simplify.
Simplify for GCD. I mean, any polynomial computations where you're doing work with rational functions, you're doing GCDs all the time. You're doing GCDs of the coefficients because you want to toss out the content. You don't want to make sure that common factors, and you want to do GCDs of polynomials, multivariate polynomials, and it turns out that that's one of the questions where the final answer might be 1, but the intermediate size of the expression grows doubly exponentially. So you need to control the size of that intermediate expression swell, and one way to do that is to take your polynomials modulo a whole bunch of different ideals and get the answers in all those different moduli spaces and then combine the answer. And so you control the size this way, and the combination winds up being 1, then you never have these gigantic sizes. So it's a crucial piece of computer algebra technology, and not just an answer for itself. Yeah. History. They decided that 10 was the right number for the initial implementation. It was a decimal-coded floating point. And they said, okay, 10 digits is what people want, and they were not using the hardware floating point at the time, and people just got used to it. One of the first things I do when I run Maple is I set digits equal 15, which means let's just use the hardware precision by default. But
it uses software floating point arithmetic by default.
It's actually fairly clever about it. If it can fit in hardware floating point, it will, but it's always translating back into its own representations, unless you tell it that the data type of what you're doing is a hardware float, in which case it'll leave it alone.
For printing, for actual content.
For printing, there's always the conversion, because I mean, you would always convert from binary to decimal anyway to print something, unless you had format hex, but we don't have format hex in Maple.
Anyone pointed out that that's insane.
Many times. Siegfried Rump said, we have to do something about this arithmetic. Well, no, it's just not going to change.
Okay.
Marcus.
10 digits. Humans have been working with 10 digits for millennia.
In fact, there we go. There we go. I like that answer. I'm totally stealing that, Marcus. Thank you. Yoink, as the kids say. Oh, there's the beginning of the religious wars question. Over the course of my career, I've come to the conclusion that it's a matter of Not actually, it's like stronger than taste. So it's a matter of personal ways of thinking about some problems. So lots of people think of programming as in a rule-based way. Here's this flow from this to this, and they find the block languages like C and Pascal and Maple and MATLAB alien. And the sense of sequence bothers them. They want to think of, we've got transformations going on. And Mathematica suits people like that very well. They prefer to program in Mathematica. Myself, I fit into the block language kind of thing, and I think of things proceeding in sequential. I like to see what's happening, and then so for me, Maple is more natural. But I have very, very good friends who write programs in both languages, and others, lots and lots of different ways of doing things. They're all fully functional. You can do anything in any one of them. It's just a question of what's more natural for you to do. It's true that at one point Mathematica would simplify series or simplify expressions by taking series, and if enough series coefficients were 0, it would say that the function was actually 0. And I know new mathematicians who got really, really upset about that because they wrote a paper called Strange Series and High Precision Fraud, where the first 300,000 terms were 0 but the next ones were not, or the first 8 integrals in a sequence of integrals were 0 but the 9th was not, and so they thought that this was like lying to the user. It's just terrible kind of thing. But I bet that strategy is right more often than not. So if 8 terms of the series are really 0, then maybe your function really is 0. So obviously not all the time, but sure. You can run anything in batch mode, right? So yeah, there's no problem with that. In fact, I have done so on many, many occasions. We were solving a heat transfer problem, flow between, so heat transfer in an annulus, a hot thing on the middle and cold on the outside, and we had massive perturbation series, and yeah, the first few attempts at writing these code, the code would run for weeks in the background. My grad student Yiming Zhang eventually made algorithmic improvements to that so that we could get series up to the order 200. We have a paper in Siam Journal of Applied Math where, yeah, we still took hours to do some of the computations, but and again, batch mode was essential. For those ones, there's an internal format, .m format, but it's not human readable. So we wrote the information that we wanted into a file. So it's perfectly possible to do that.
All right. Thank you, Robert.
Thank you very much, Yuri. And thank you very much for listening. And Nadia and I will be enjoying our coffee, so if you have more questions, we have more.